Okay, hello everyone, good morning. Welcome to the first session of the second day, and the session is called Bitcoin Bridges and Proof of Work. The first talk is going to be by Robin Linus from Stanford and Zero Sync. The title of his talk is Efficient Bitcoin Bridges Using Garbled Circuits.
Good morning. I'm going to talk about BitVM 3 today, which is a way to build better Bitcoin bridges. It's a joint work with these people. And first of all, why do we need BitVM at all? Well, we want to bridge Bitcoin to other systems. That is because we all know layer 1 doesn't scale, and in general, blockchains don't scale very well. And we would like to have the Bitcoin asset on side chains, roll-ups, maybe bridge it to Ethereum, and in general, bridge it to all kinds of other systems, because that enables rapid innovation, which is not possible on the main layer because the main layer is hard to change. Cheap experimentation, we can try different scalability solutions, and it also enables privacy solutions. And the previous state of the art for bridges was just trusted multi-sig bridges. You can do like slightly better with expensive over-collateralized bridges, but they're not really practical. And now the question is how to build better bridges. In particular, without a consensus upgrade, because Bitcoin is extremely hard to change, and it's very hard to get any consensus on any update. Even the most simple updates are pretty hard in Bitcoin. So what we're actually doing here is we are solving a people's problem. What do we want? Well, we have Bitcoin, and we have some sort of side system, and we want to bridge Bitcoin into the side system. That is actually the easy part. That is not that hard. The hard part is that eventually, after the Bitcoin has circulated in the side system, someone wants to bridge back and wants to redeem Bitcoin in the main chain. And for that, they need to convince Bitcoin that they are actually entitled to take money out of the bridge. And that's the hard part. And the canonical solution in the altcoin world is you just use a snark. You use a validity proof, and that allows you to convince the Bitcoin chain that you are actually allowed to take money out of the bridge. However, how do you verify a snark in Bitcoin? That's not quite easy, because there are all kinds of challenges and limitations in Bitcoin. First of all, the scripting language is extremely limited. The coolest thing we have is an addition opcode, so we can add 32-bit numbers, which is not that sophisticated in comparison to, for example, Ethereum, where you have opcodes for pairings. So this is way more low level. In general, the script size is linear in the length of the computation, because there are no loops. Bitcoin script is intentionally not Turing complete. The script size is limited by the block size, and in general, block space is expensive. And if you would just naively implement a snark verifier in Bitcoin script, you would end up with 1 gigabyte of script, which is, of course, orders of magnitude bigger than what fits into a block. So how do you verify a snark in Bitcoin, even though you cannot really do it in the scripting language? And the answer to that is BitVM. In general, BitVM is a way to verify snarks in Bitcoin, even though the scripting language actually doesn't allow it. So it's a workaround, a hack. And how does that work? Well, in general, as I said, we want to have snark verified bridges without any consensus change, and the key idea is that we're going to use optimistic computation for that. So basically, you just claim this snark is valid, and if it's invalid, someone can succinctly disprove you. That has the advantage we do not have to verify the entire snark on Bitcoin. We just have to be able to verify a counterproof that it is invalid. And that is generally much cheaper than actually verifying the snark. And it's just as good, at least in theory. As I said, yeah, the idea is don't verify the snark, falsify incorrect snarks. We accept that bridge operation is permissioned. So we do have operators who operate that bridge. But that is fine as long as challenging it, as disproving a malicious operator is permissionless. So anyone can disprove, but there is only a dedicated set of people who can operate the bridge. And the general idea is the operator asserts to a proof, and then anyone can read that proof from the chain, and if it's invalid, they can slash the operator. And if not, the operator can withdraw from the bridge after some timeout. So that's the general high-level mechanism. The operator asserts to a proof. People can read it from the chain. If it's incorrect, they slash them. And if it's correct, then the operator can withdraw from the bridge after some timeout. How does that look in Bitcoin transactions? In Bitcoin, we have to express smart contracts in transactions. And it's roughly like Alice deposits money into a multisig. It's not really a multisig, it's an N of N, and it's to emulate covenants, but it's not important what that is in particular. But the key idea is that we have a withdraw transaction that is already defined during deposit time. And in theory, you can execute the withdraw transaction anytime. However, the withdraw transaction has another input. It depends, Too bad. You see the green arrow? It depends on a second input. So you can execute the withdraw transaction only if you also have that second input. And where does that second input come from? Well, that comes from the so-called kickoff transaction. And in that kickoff transaction, the operator has to assert to a proof. So they can execute the withdraw transaction only if they have executed the kickoff transaction previously and then also waited for 1 week. And that is exactly the challenge time. And during that 1 week, everyone can read that proof from the chain, validate it, and if it's incorrect, they can derive a succinct for proof and disprove the operator to burn this coin and basically rendering the withdrawal transaction obsolete. That's the high-level mechanism of how the bridge contract works. And we have a copy of all of these transactions, like the withdrawal transaction, kickoff transaction, disprove transaction for every operator. And we assume one of the operators is live, so one of them will succeed at withdrawing. That's the high-level idea of how we express a bridge contract in Bitcoin script. Now, the guarantees. It is still somewhat of a federation, but we reduce it to a single honest member. We also need these cosigners to emulate that covenant. And we can have up to 100 plus operators. And the guarantees are that nobody can steal money from the bridge as long as one of these cosigners is honest. And the bridge is live, so people will get their money eventually as long as one of these operators is live. And of course, you can become a member, so you could be an operator or you could be a cosigner, and then from your perspective, it's completely trustless. Of course, it makes only sense for people who have a large stake in the site system, for example, an exchange or liquidity providers and so on. The rough difference between BitVM2 and BitVM3 was in BitVM2, we did it with on-chain computation. We basically chunked up the script in a way that allowed us to disprove an incorrect execution on an incorrect snark succinctly enough to somehow fit it into the blockchain. However, that was very expensive. In the worst case, you needed to buy an entire block of block space. It required non-standard transactions that you couldn't broadcast in the peer-to-peer network. And in BitVM3, things became way nicer because now we do it all with off-chain computation in garbled circuits. And that is very cheap in comparison, and it fits into standard transactions. Just to give you an overview of how drastic the improvement is, in BitVM2, this assert transaction was roughly 2 megabytes, and the disprove transaction, so to disprove an incorrect snark, it was 4 megabytes. So in total, the worst case cost was 6 megabytes. The happy path was still pretty efficient, but the worst case cost, which you had to be able to pay for, was almost 1.5 blocks of block space. So it was extremely expensive. And now with garbled circuits, it's vastly more efficient. The assert transaction can be shrunk down to 8 kilobytes. And the disprove transaction is just 200 bytes, which is almost a 1000x improvement, roughly. And how do we do that? Well, we do that with using garbled circuits, which originally have been invented for multi-party computation. We are using them to have something called conditional disclosure of secret. So we want to disclose a secret under a specific condition. The rough idea is we have some black box, and you can feed a snark into it, and the black box validates the snark, and if the snark is incorrect, the black box gives you a secret. That is, on a high level, the rough primitive that we would like to have. And that looks a lot like witness encryption, and we all know witness encryption is black magic. But we can do a similar thing with garbled circuits, which can be used for a weak form of witness encryption, an interactive version of witness encryption, which is good enough for our case. So it works such that during the setup, you agree on this black box off-chain, like you just exchange that data off-chain. Then during withdrawal, the operator asserts to a snark proof on-chain, and then the challenger can evaluate the input using that black box. And if the snark is incorrect, they learn the secret, and this secret is the fraud proof that they're going to use to slash the operator, to prove that the operator lied. So knowledge of that secret is a proof that the operator lied, and it's a proof that the Bitcoin blockchain can understand. That's the key idea, that you just need to reveal that secret to disprove an operator, and you don't need anything else. How do garbled circuits work on a high level? We have a truth table here. This is just an AND gate. And the first step is we just replace the truth values with labels. So where there was 0, we now have A0. Where B was 0, there is now B0, and so on. And these labels are known only to the garbler or to the operator. And we have an encryption scheme, and we encrypt every row with the inputs, or like we encrypt the output of every row with the inputs. So here on the left side, A0 concatenated with B0 is the decryption key or the encryption key for Z0. So if you learn the inputs A0 and B0, you will be able to decrypt C0. And we do that basically for every row. So A0 and B1 also encrypt C0, A1 and B0 also encrypt C0, and A1 and B1 encrypt C1. So if you learn a specific input, for example, A is 1 and B is 0, then you go into the corresponding row, and you decrypt the corresponding output value. And this is how you garble a single gate. And once you know how to garble a single gate, you can compose this. It's important to have a verifiable encryption scheme. That's an important point. Like, since I give you only these cipher texts, you don't know what they mean. So I need to prove to you that you can actually decrypt them into the corresponding output label if you know the corresponding input labels. So we need some sort of verifiable encryption scheme to have a verifiable garbled circuit. And once we know how to garble a single gate verifiably, we can just repeat this process to then compose a lot of these gates into an arbitrary circuit. So, and the interesting property that we now have is that a specific set of input labels will reveal the corresponding output label. So if I have a set of input labels that correspond to a correct, a valid snark, then I will learn the true value. Like I will learn here, that's roughly the function signature of a verifier. Like you have the verify function, you feed a proof in there, and it returns true or false. And if the input is a valid snark, I learn the true value. And if the input is an invalid snark, I learn the false value, which is our fraud proof. And yeah, as I said before, like the bridge operator, they publish a snark, which are the inputs to the circuit now. Challenger verifies that snark in the garbled circuit. They go through all the gates and learn the output label, and then they take the output label as input to the next gate, and then they can walk through the entire garbled circuit. And at the end, they either learn the false label, which is the fraud proof, or they learn the true label, which is just nothing. And this is an extremely efficient protocol, as I said, because the on-chain cost is reduced to basically nothing, especially for disproving, because for disproving you just need to publish that secret. However, what is the off-chain cost? How expensive is this black box? And that is actually one of the main research questions people have dealt with. There was quite an evolution of garbled circuit schemes in like the BitVM adjacent research community. We first started with Yao-style garbling, which is already from the 80s. The good thing about it is it's very simple. And we have an implementation already, which is open source. However, the bad thing about it is like the circuit can be like 100 gigabyte, and the setup time is 30 minutes. And you need such a circuit for every operator, for every deposit. So this is very inefficient, and it easily goes into the terabytes in practice. So people were not satisfied with that, and they started doing all kinds of interesting research. Liam Egan published in 2025 the Glock scheme, which reduced the circuit size already to 100 megabytes or so. That was quite an improvement. However, the bad thing about it is it requires permission challenging. There is only a permission set of people who can actually validate or like run the circuit. And you need to define them during setup. And yeah, that creates a one-of-n assumption for validation, which we would not like to have. And it had like a few exotic cryptographic assumptions. Not too fancy, but not super desirable. And then Liam improved on that again in 2026 with the Argo scheme. And that is much simpler, or like much smaller in particular. It reduces the size down to 32 megabytes roughly, and it enables permissionless challenging. A drawback of it is that the on-chain footprint is a bit larger because yeah, you need to publish both the x and y coordinate of the curve points. Of course, you could do that in the garbled circuit as well. Like you could decompress the curve point in the garbled circuit, but that would blow up the size of the garbled circuit again, unfortunately. So we roughly have a 2x larger on-chain footprint, but the off-chain footprint is dramatically smaller. And then following on that, there was the Babe paper, which you're going to hear about in the next talk. It combined the Argo MAC with linear witness encryption, and that reduced the circuit size. I think 50 megabytes is not even true. I think you reduced it even further. It's a very simple scheme. It's much simpler than Argo. That's a nice advantage. The drawback of it is that it is permissioned. Like the set of validators is permissioned again. And then there was another very interesting work that was like a follow-up to Argo and Babe, and they further reduced the circuit size of basically both Argo and Babe to less than a megabyte. So now it's extremely efficient. So we started at 100 gigabytes or something, and within 1 or 2 years, people brought it down to 1 megabyte. And now off-chain computation is pretty efficient in Bitcoin. Here's a rough overview of the schemes that people have worked on and the different dimensions that we judge them in. This is just as an overview. Don't want to go into too much detail here. Another dimension of this is the on-chain cost. Like, how do we actually publish that snark? Because you cannot just publish the snark without any encoding. You cannot just put like the bits of the snark into the chain, and because you need to have them in some encoding that allows you to feed them into the Garbled circuit. Essentially, you need to sign them in some way. So this is this part here. This kickoff transaction. Here we need some encoding to publish the snark. And how do we encode this? Well, the most simple way you can think about it is basically a Lamport signature. The problem is that's roughly 80 bytes of overhead per bit. So it blows up the size of the proof by roughly 80 bytes per proof bit. The good thing about it is it's very simple, and it's exactly the same encoding that Garbled circuits use. So the inputs of Garbled circuits, they are basically Lamport signed. And this is the most simple scheme that you can verify in Bitcoin script. So that was like the first approach that people tried. You can optimize it a little bit by using Winternet signatures instead of Lamport signatures. That gives you basically a 2x improvement. That is because of the intricacies of Bitcoin script. Of course, in theory, Winternet signatures would allow you to compress it even further, but that's not possible in Bitcoin script, unfortunately. The best you can do in Bitcoin script is roughly a 2x improvement. There is a drawback, though, because if you have Winternet signatures, you now need to translate the Winternet signature into a Lamport signature, because Lamport signature is like the format of the inputs of Garbled circuits. So you read the Winternet signature from the chain, and then you need some sort of off-chain translation from Winternet signature to Lamport signature. And of course, that increases the amount of the off-chain cost a bit. And then people came up with another idea. They used adapter signatures, which has been a topic in Bitcoin for quite a while. It's similar to hash locks, actually, but based on signatures. And this brings it down to roughly 8 bytes per bit. It has the same drawback that you need some sort of translation from adapter signature to Lamport signature. And there is another drawback. It requires some trusted setup. For a adapter signature, you need a counterparty. So now you need to interact with a counterparty to set up these bridge contracts. There's a bunch of remaining challenges. First of all, the deposit liveness. Currently, we need this co-signing committee to deposit coins into the bridge, and that requires liveness of that committee. That's unfortunate. The good thing is people cannot lose money, even if the Covenant Emulation Committee is not online, then you just cannot deposit. But it is, of course, a bit annoying that we have this n/n assumption for liveness. It would be great if we had some sort of consensus change. People are talking about covenants, opctv, template hash is another one that might actually get through. And another big topic I have not touched here because of time, we need, if we are using something that has DA on Bitcoin, data availability on Bitcoin, for example, a rollup that publishes its data on Bitcoin, we need a Bitcoin Lite client to introspect the chain, to read data from the chain. And we have a few solutions for that. One is permission challenging. However, that reduces the one-of-n assumption for safety again, which is, of course, unfortunate, and that's why we don't use it. We came up with a Lite client that enables permissionless challenging. That's also in the paper. The drawback of that is it requires periodic commitments, so the operator needs to make commitments every 2 weeks. There is another way. We can do like transaction introspection with a hack called BinoHash. However, that is like very quirky and uses all kinds of features of Bitcoin that are outdated and that people actually discourage users to use. Another thing is withdrawal liveness. That is, in general, a fundamental limitation of our approach, that we have this dedicated set of operators who can operate the bridge. And if none of them is live, then nobody can withdraw from the bridge. So that is unfortunate that we have this one-of-n assumption here. We can solve that only with actual consensus changes, something like great script restoration or simplicity or something like that. Or maybe with witness encryption and pipes, which the alloc init team is working on. Summary, BitVM enables better Bitcoin bridges. It can improve privacy, scalability, and programmability. BitVM 3 with garbled circuits enables efficient off-chain computation. It's a roughly 1000x improvement over the previous work with BitVM 2. The Argo scheme gives a 1000x improvement in on-chain cost, in off-chain cost in comparison to like the naive YAO-style scheme. And now snark verification on Bitcoin is very practical and cheap. That's the main takeaway. There are a few remaining challenges regarding livety and safety trade-offs, and but I hope, or like I think people will keep on working on that, and we will see more interesting work to save these things. All right, thank you.
Thank you. We have time for 1 or 2 questions. If anyone wants to ask questions, please come up to the mics here. Meanwhile, I'd request David, the next speaker, to set up.
Thanks for the nice overview. So in terms of the remaining challenges, how does the landscape look like considering post-quantum security?
Yeah, that's a good point. I hope nobody was asking that. Yeah, with post-quantum security, things become much more complicated, and the main reason for that is that we have this huge blow-up factor for publishing the proof in the chain. So currently, it's 8 kilobytes to publish a gross 16 proof. If we now use a post-quantum scheme, which is like 1,000 times bigger, then we end up with like 8 megabytes or something. And it's still theoretically possible, but now you need to buy like 2 blocks of block space for that. You can tweak it a little bit by like making it optimistic, like making proof publication optimistic. So you just publish the statement, and if the statement is incorrect, you challenge the operator to also publish the proof, which you then disprove. But yeah, it makes the scheme more complicated and way less efficient, of course.
One more question.
For verifying that the garbling was done correctly, are you still using cut and choose, or now things are simple enough that you can actually use snarks?
People are mostly using cut and choose, yeah, because it's just the simplest way. The problem is that we need like a lot of these garbled circuits, since every operator needs a garbled circuit for every deposit, and you want to set them up in advance. Like you basically estimate how many deposits they're going to be, like 10,000 or something, and then you generate 10,000 garbled circuits during setup time, such that you don't have to interact with the operators during deposit time. And that's why we care about the setup being efficient for tens of thousands of garbled circuits, and the most efficient way we know is cut and choose.
And the numbers you quoted include the cut and choose overhead? Or?
Yes, yeah.
Oh, cool, thanks.
Actually, Liam came up with a scheme that combines cut and choose with some snark techniques, such that you get public verification with just 2 circuits that you have to store, instead of, I think, 120 or something, which for naive cut and choose.
Okay.
All right, thank you.
Thank you very much. Let's thank the speaker.